Something you've probably noticed about ROS is that it does not interface directly with hardware. There does not seem to be any motor or sensor libraries. That's because ROS is designed to be a middleware layer. Its goal is to provide a modular and scalable framework for building software. For hard, real-time control like pulse width modulation and meeting strict sampling deadlines, your best bet is to use a microcontroller where you have control over such processes. While ROS provides the software framework, we can set up communication with such microcontrollers to start building our actual physical robot. We've made it to the end of the course. Hopefully by now you have a solid grasp of the fundamentals of ROS2 and are comfortable writing nodes in either Python or C++. We will end this series by providing a demonstration of ROS running on real hardware and how you might communicate with microcontrollers to meet real-time control requirements. We will use a Raspberry Pi 4B for this demo, but you're welcome to follow along with any single-board computer that is capable of running Ubuntu. Many single-board computers are capable of controlling hardware. You can often toggle pins and communicate over buses like I2C to talk to sensors. This might be sufficient for simple robots, but as things get more complex, you will often find that you need faster speeds and the ability to control more peripherals. Also, you'll likely need to meet hard, real-time deadlines, like toggling a pin within microseconds to make a particular piece of hardware work. General-purpose operating systems, like Linux, are not designed for this. Most distributions use non-deterministic scheduling policies and can often take too long to handle hardware-based interrupts. As a result, you have no guarantee of timing when you need microsecond precision. That's where microcontrollers come in. They are designed to interface directly with hardware, and you have low-level control over the processor and interrupt handling. So we use a combination of the two. The single-board computer handles the high-level processing in ROS nodes, which then communicates to our microcontroller that handles the low-level functions like motor control. Note that micro ROS exists. This is for running a lightweight version of ROS on powerful microcontrollers, which gives you access to all of the nodes, topics, and services that you've seen so far in ROS. However, it requires some unique setup and should be considered its own framework. As a result, we won't cover it here. Perhaps it would be a good topic for a future series. So we'll stick to using a combination of single-board computer and separate microcontroller for now. How you establish communication between the two is up to you. You could use a simple pin to trigger events, UART, SPI, I2C, CAN, and so on. For our demo, we'll keep it simple by sending serial commands over USB. Here's how we'll set up this demo. We will have the Raspberry Pi run ROS2 Jazzy in Ubuntu 24. We'll write a very simple node that periodically sends out serial commands over USB to a connected Raspberry Pi RP2350. I'll stick to Python for this demo, which means we'll need the Pi serial package. We'll create a simple program in Arduino that interprets our serial messages and controls a couple of pins for each motor. Those pins will be connected to the direction and PWM pins of the individual motor controllers on the XRP board. The Experiential Robotics Platform, or XRP, is a rover-style robotics kit designed for educational purposes. It has a controller board with a built-in RP2350 that acts like a Raspberry Pi Pico. The board also has motor driver hardware connected to some of the RP2350 pins. We'll add a custom 3D printed cage on top that holds a large power bank and a Raspberry Pi 4B. I put a PiCam 2 on as well for a more advanced demo later. Note that I had issues getting the PiCam 3 to work as it uses a different chip that does not have support in Ubuntu 24 by default. We'll connect the XRP board to the Raspberry Pi and then apply power from the battery. For Arduino, we're going to be using this Arduino Pico board library from Earl Philhauer. We're not going to use the official Arduino library because that was built on Mbed OS, which has been deprecated. And this library, even though it's a third-party library, is not built on Mbed OS. If you scroll down, you can find information about how to install it. So we're going to go to Arduino. I've got a blank file here. We're going to go to File Preferences. If you go to Additional Boards Managers, you can see where that board's library is installed here. So github.com, Earl Philhauer, Arduino Pico, releases, download global, package RP2040 index.json. Click OK, click OK. That should update the information in Arduino so it knows how to find that board information. Now let's write our serial driver. We will first define a debug flag that we can turn on or off. This will allow us to print stuff to the console that will help us debug any issues in this firmware. I found that with all the weight on the XRP, especially that big heavy battery, nothing really moves, or the robot doesn't move, until you hit a PWM of at least about 120. So our actual PWM values are 0 for not moving, and then 120 to 255. That 1 to 119 is just kind of useless area where the motors will hum and not do anything. Then we need to set up some buffers in order to capture information over the serial line that's coming from our Raspberry Pi. I will set up max characters of 64. You may want this larger, but I don't expect to have any more characters coming across the serial line per drive update. And then we will expect a number of values up to 4 that we need to parse. This will be PWM and direction for each of the motors. Then we will define some pins. We will need the direction and PWM pins for the left motor and the right motor. If you look at the XRP schematic from SparkFun, you can find where these pins are connected to the individual motor driver chips. So the direction pin for the left motor driver is pin 35, PWM pin is 34. For the right motor, we have the direction pin of 32 and the PWM pin of 33. Next, we construct some buffers to store information coming across that serial line from the Raspberry Pi. We have our input buffer. This is just storing the raw characters. Then we have the actual values. Once we've parsed the characters, the drive values get put into this vals array. And then we just store this buffer index value that's going to be a global for here. It's up to you how you want to send information over the serial line. As I've mentioned before, you could use SPI I2C, so you could set up your microcontroller to be a client that attaches to a bus. But for our project, a very simple serial over USB gets the job done. What we're going to do is send the values over the serial line. They are going to be in comma-separated values, so a comma between each one, and then each line will end with a new line character. That's how we know that the whole message has been sent. We will use this string tokenizer function that's in C, in the standard C library, to break apart our string. So we give it the input, tell it how to divide up the string, and then we get a pointer to that initial token. Then we will loop over the other tokens in that string. So we should have 4 tokens, 1 for each value, and we will do so up to the maximum number of tokens given, which should be 4. So expect 4 values to come through. We will convert that first token we got using the A2I function, which converts a character array to an integer. And we're just going to say that we can't send floats over this. We have to send integers, which is fine. We will store it in that vals array, increment the val counter, and then break apart the next token, and then continue that loop until we reach the end of those values. In our setup function, we're going to initialize our serial. We will give it a baud rate of 115/200. Then we will configure all of our drive pins. So all of these pins need to be output since we are essentially controlling the signals to those driver chips. Next, we will tell the robot not to move. These PWM pins should not be toggling, but just in case, we will explicitly set them to 0 so the robot doesn't move when it first boots up. Then we will initialize the values array, and these should all be set to 0. In loop, we won't do anything unless we receive some bytes over the serial port. Then we will read in 1 byte at a time from the serial port. If the last character, or if any character, is equal to that new line character, we will set wherever the index is in that input buffer to the null character, so we know it's a complete string. Then we will call that parse CSV ints function we just wrote, pass it in that buffer, and reset the buffer index back to 0. Otherwise, if we receive something that's not the carriage return character, as we generally want to ignore that, and as long as the buffer index is less than the max number of characters -1, remember we need to leave a space available for that null character. All we're going to do is just put that received character into the input buffer and increment our buffer index. If the debug flag is set, we will print out the received message to the screen, but we're going to do so after it's been parsed. So we should have the correct values in that vals array, and we will just cycle through and print them to the console to make sure that parsing was done correctly. Next, we will set the motor direction. To get that, we will look at the third and fourth elements in that vals array. If they're greater than 0, set the LDIR and RDIR to 1, otherwise set it to 0. Ideally, you should only be using 0 and 1 for this, but just in case, this makes sure those values are explicitly set to 0 and 1. Then we will use digital write to set those pins to either 0 or 1. Then we will set the speed of both motors. We will do that by looking at the first and second elements of the vals array. If they happen to be negative values, they shouldn't be, but just in case, we will make sure to set them to 0. Otherwise, they're set to their actual values that were sent in. Then we will map the values. Ideally, the user sends in something between 0 and 100. So 0 should remain 0, so the motor should be off, but anything between 1 and 100 should be mapped to our minimum speed to 255. So it expands out linearly to those values. Remember, that's to avoid anything between 1 and 119, where the motors just kind of hum and do nothing. But the user should be able to set anything between 1 and 100, ideally kind of like a percentage, to get the motors to actually spin and the robot to move. For whatever reason, I could not find a good explanation of this, so if you happen to know it, let me know in the comments. The PWM signal is actually inverted when the driver is set to go in reverse. So if either LDIR or RDIR is set to 1, that means we want to move the motors in reverse. We need to subtract our speed, our PWM speed, and this is the absolute PWM speed between 0 and 255, from 255 to invert that PWM signal. I've not fully exactly tracked down why this is occurring with those driver chips. Finally, we set the actual motor speeds. This performs the PWM on those pins and holds that value until we set them the next time. That's it for our Arduino code, so Control S to save, put it somewhere on your computer if you wish. We need to upload this to the XRP, so you will want to hold boot and reset buttons, and then release the reset button while still holding boot. That should put it into the bootloader mode. It should show up here, but if not, you can select other board. The XRP is based on the Raspberry Pi Pico 2W board, so feel free to select that, and your ports should show up here. But because we are in bootloader mode, it's actually UF2 bootloader, which is not a serial port. So we should be able to upload this to our Arduino. Looks like I misspelled received. Something after C. Oops. And let's try uploading again. With that done, you will probably need to reset your Pico or your XRP board again. Notice that I'm using the release version of the XRP. If you have the beta version, if I recall, this is based on the Pi Pico, not the Pico 2. So this is for the actual release version of the XRP. But with that done, I've reset the board. You can come down to Serial Monitor. You need to select the new serial monitor after you reset the board. Let's say OK. Now we have it. The message format is left speed, comma, right speed, comma, left direction, comma, right direction. And if I recall, I believe you do need the spaces between the commas because that's how we're parsing it. This isn't a very robust parser, but it gets the job done. So 50, 50 should be about half speed. 0, 0 should be forward for both motors. If you send that along, that should cause your motors to spin forward. And if you want them to stop, just send zeros. With that done, we can now write our ROS node on the Raspberry Pi. If you're running into issues where the motors aren't turning, it turns out that we should not actually be using Raspberry Pi Pico 2W. There is a specific board that if you go to select boards, you type XRP and you should see the 2 XRP controllers. I'm using the newer XRP controller, it's not the beta one. And we will select that and click OK. Then put the board into bootloader mode by holding boot, pressing reset, and then letting go of the boot button. From there, we can upload and then connect to the serial monitor. You might need to reset the board again to get it in the right mode. And let's try sending 100, 100, 0, 0. And that should send the motor spinning. When you're flashing your Raspberry Pi, you will want to use other general purpose OS, go to Ubuntu, and I recommend using Ubuntu Server 24.04 long-term support. I found this is the easiest way to install ROS2 on a Raspberry Pi. You're welcome to try installing it in Raspberry Pi OS, but ROS generally recommends Ubuntu Server. You can try the desktop. This just takes up more space. You ultimately won't need the GUI. And if you really want one, you can install a lighter weight one that doesn't take up as many resources on your Raspberry Pi. So this is the one I recommend using. Once it's installed, you'll probably need a monitor and keyboard to install something like SSH, and you will want to follow these instructions to install ROS2. Here's the page for installing Jazzy. Go to deb package. This walks you through the steps of installing ROS2 on Ubuntu, which should work on your Raspberry Pi. Once you've installed ROS, and you can install something like SSH or an SSH server, this is where you can start development. My recommendation is to use something like VS Code. Go to extensions, install the remote SSH extension, and you can log directly into your Raspberry Pi. So I've done that here. Here's my Raspberry Pi file system. I've got a terminal on ROSbot, and I'm logged in as the Pi user, and I can edit files here. This is a great way to interact with your Raspberry Pi when doing things like programming. You'll first want to do a sudo apt update to update all of your packages. Once update is done, we will need to install a few tools. The first is net tools that allows us to do things like ifconfig to get your IP address. We will need the open SSH server. If you are connected in through VS Code using SSH, you've probably already installed this. We will also need virtual environments found in Python. So Python 3. Whatever version you're using, Ubuntu 24.04 should come with 3.12. And we need Python 3 pip so we can install some Python packages. Enter your password and that should install everything. These should already be installed for me. Once that's done, if you have not done so already, you will need to enable the SSH server. So sudo systemcontrol enable SSH. Then sudo systemctl start SSH, and you should be able to check the status of that with systemctl status SSH. That should be active and running. Q to get out of that. If you go into .bashrc in your home directory, I'm going to use nano to do this because I'm too lazy to open it in VS Code. You will want to scroll down to the bottom and add this line here, source opt ROS Jazzy or your particular distribution, setup.bash. That gives us access to all of the ROS2 tools. I'm going to control X and yes to save that buffer. If you don't want to refresh your terminal or relog in, you can say source, tilde for your home directory, and then .bashrc. With that done, it's finally time to set up our package. I'm going to create a folder for our workspace. I'm going to call this pybot_ws for workspace. This will be put in the home directory, and in there I will put a source directory. Let's go into that workspace. We will call an initial callcon build that should fill out some of the boilerplate files and folders for us. Once that's done, if we come up here, refresh our files, we can go to pybot workspace. You can see this boilerplate filled out for us. So we've got build, install, log, and sources where we're going to put our source code. Let's go into source, and we will say ROS2 package create, build type ament Python, pybot package. We're only going to be working in Python for this one. If we refresh, you should see the pybot package inside of source. Let's navigate out of the source directory, and we will create a Python 3 virtual environment. Python 3 now requires us to use virtual environments when installing third-party packages. So we will say Python 3-m vn for the virtual environment package. Let's give it a name of vn, and we will say system site packages. This allows our virtual environment to access the global or system-wide packages that are already installed outside of the virtual environment. I found that this is necessary when working with a lot of the ROS2 stuff because those are considered third-party ROS2 Python packages. Once that's done, it's often helpful to create a file, a blank file named callconignore in that particular folder. So if we refresh, you can see venv here. When you say callcon build without specifying a particular package, there's a chance it might look in this venv folder for packages. And if it finds this file, this very specifically named all capital letters callconignore file, it will ignore this and not treat it as a source for various packages. It's often recommended if you're putting a non-standard folder inside of your workspace that's not build, install, log, or source, that you put this file in there, and it can just be empty. Now, anytime we go to run something, you will want to say source venv bin activate from that workspace directory, and notice we are now in this Python virtual environment. Very important package we need here is PySerial. Let's call python3-m pip install PySerial. Notice that we're doing this inside that virtual environment. That should install the serial or PySerial package for us. I have already installed it, so we don't need to wait again. You will often find that the PySerial package doesn't work without running your script in administrator mode or with sudo. That's because the current user, Pi in this case, is not part of the dial-out group. PySerial looks to see who's in that dial-out group, and by default, your basic user, Pi in this case, is not in there. So to fix that, we will call usermod to add the current user to dial-out. With that done, we can finally write our source code. Let's go into PyBot package. This is where we keep our code. Let's create a new file, and I'm just going to call this serial test. This is a very basic node. We will import the things we need from RCL-Pi, which you've seen before in our various other nodes throughout the series. So we need RCL-Pi, RCL-Pi.executors, and the external shutdown exception in there. And we need RCL-Pi.node, and in there, the node class. Then we import our PySerial package. This is just import serial. Let's define our driver demo. And all we're going to do in here is just move the robot around. In our constructor, we'll call the superclass constructor. We give the node the name driver. Then we will declare a few parameters. In this case, we will declare the serial port, so that can be changed by default in the Raspberry Pi. That should be dev tty acm0. We will set a default baud rate of 115200, but that can be changed if you, say, for example, change that in your Arduino code. And then a timeout value of 1, which we will need later. After that, we'll initialize the serial port. We do that with serial.serial. We give it the port, and we will just get that parameter value. We then set the baud rate. Again, we will get that parameter value, and then set the timeout so that the serial library will wait a little bit of time before failing on us. In this case, it should just be set to about 1 second by default. We're going to set up a very simple state machine to drive around. We're going to do this with non-blocking code in our callback function. We're going to have 3 basic states where it turns left, drives forward, stops, and then repeats. Finally, as you've seen before, we will set up a timer to periodically call our driver callback function. I'm just going to hard code this to 10 times a second or a 0.1 second period between callbacks. In our callback, we will first get the amount of time that's elapsed since the previous timestamp was gathered. If that amount of elapsed time is greater than 1 second, we have to compare this to the amount of nanoseconds given. Then we will increment our state counter and get a new timestamp. Here is where we increment that state value, and if it's 3 or greater, we'll just reset it back to 0, so that gives us 3 states to work with. We will also print that new state value to the console. Here's our actual state machine. So in the first state, if that state value is 0, we will turn the robot, so we will have the right speed be a little faster than the left speed of the motor. I'm going to copy this and paste it twice. And I will fill out the rest of that state machine. So in state 1, we're going to put the motors at full power. We will say go forward here. And then we will say stop the robot. And actually what we want to do to turn the robot is we want to set one of these to go in the opposite direction. We need to construct the message to send out over the serial port, and we will go ahead and write that. So this message is the left speed, comma space, right speed, then the left direction, and right direction, as we saw when we tested the Arduino program. Note that we need to specifically include the new line character here, otherwise that does not get sent. And then we will say dot encode so that this gets encoded properly for being sent over the serial port. I'm going to explicitly call the serial ports.flush command here to make sure that everything gets written out before we do this loop again. Here is the very common boilerplate that you will probably have seen a lot of times by now, and this defines our main function that initializes and runs our node. It instantiates it, runs it. If something happens where we press, say, Control-C to stop it, it gracefully shuts everything down. We also see if the executable name is equal to main when we're running this from directly in the Python environment. And if that's the case, we will call the main function. Save this code. With that done, let's go to package.xml. We need to add our dependency here. The only dependency we have is RCL-Pi. We're not using any other ROS packages. Let's save that. Then in setup.py, we need to add our executable that we just made. And we're going to say driver demo equals pybot package.driverdemo:main. And I do have an error here. I did not want to call this serial test because that was actually for testing serial data. Let's call this driver demo. That should line up with all of the naming we've been doing. So with that saved, let's make sure we're in our workspace in our console. And we will say callcon build packages select pybot package. Hopefully that builds successfully. When you want to run this, the order of operations is to first source your virtual environment activation script. So now you're in the Python virtual environment. Then you will want to source the setup.bash that's in the install directory. So now you have access to all of your executables and packages that you've just created within the ROS2 environment. From here, you just say ROS2 run pybot package driver demo. That should fire up and start communicating with the Arduino board, assuming you have it plugged into one of the USB ports on your Raspberry Pi. All right, it looks like I've got an error here where it's not going to the states. When I come back to my code, the first thing I forgot to do is set that to state 2. And in fact, what we probably want to do is change this to else, so it captures anything that's not one of these states. Now let's try building this again with callcon build. Once that's done, we can try running again. Remember that I'm in both virtual environments. And this looks more promising because it got to state 2. All right, it looks like we have a situation where left speed isn't getting set. So let's make this explicit. You will set everything to 0 just in case, and we'll know if we get to this block. The other thing we can do is instead of doing this catch, you can modulo with 3 to make sure it is 0, 1, or 2. Let's save. We will build again. And let's try running it, see if the same issue occurs. Looks like we are getting caught in those states. So this was a useful catch. Oops, I forgot to get rid of that plus sign. Let's save that. Build again. Let's run it again. Hopefully this works. We have state 1, 2, 0, 1, 2, 0. It looks like it's cycling through the states correctly. Now let's flip the switch on the XRP board to enable the motors and see what happens. If you set up SSH on the Raspberry Pi, you can log into it remotely in order to start your ROS program, which means you don't need a full keyboard and monitor setup. The program should start and the node should periodically tell the Arduino program how to control the motors. The robot should start, stop, and turn, just like we told it to. That might seem like a lot of work for something we could have just done in Arduino. But remember, ROS is all about scaling your robot applications to much more complex configurations. That means we can introduce things like vision processing and AI, along with the powerful TF2 framework for controlling robots with lots of moving parts. I've put together this color tracking application using OpenCV. It looks for the largest blue blob in the frame and constructs a bounding box around it. I built a ROS node around this tracker that periodically publishes the bounding box results to a topic. A driver node subscribes to that topic and figures out how to drive toward the bounding box by sending out motor commands to the Arduino program we developed earlier. Now the robot will look for blue objects and attempt to drive toward them and stop when the object reaches a certain size in the frame. It will even back up to maintain that apparent object size. This gives me a unique, fun way to interact with my robot. If you'd like to build this demo, check the description for a link to the code and some instructions. I hope this gives you an idea of how you can control low-level hardware using ROS. It usually requires integrating third-party libraries and talking to something like a microcontroller over a communication bus. Thank you for sticking with the course until the end. I hope you've learned a few things about building ROS applications and had fun along the way. Good luck with your future robotics projects and happy hacking!